Hi, good afternoon, everyone. We're very pleased to have Oded Regev with us giving our next talk. Oded Regev is a silver professor at the Courant Institute of Mathematical Sciences of New York University. Prior to joining NYU, he was affiliated with Tel Aviv University and ENS Paris under the French National Center for Scientific Research. He received his PhD in computer science from Tel Aviv University in 2001. He's an ACM fellow, the recipient of an ERC starting grant in 2008, the 2018 Gödel Prize, the 2019 Simons Investigator Award, as well as Best Paper Awards in Stock and Eurocrypt. His research includes applications of machine learning in biological sciences, theoretical computer science, cryptography, and quantum computation. He's made notable contributions in the area of lattice-based cryptography, where he introduced the learning with errors problem, which forms the basis of post-quantum cryptography. And on a personal note, so the learning with errors problem is what gave me my PhD. So I'm not on the streets because of this work. So, I also owe him some special gratitude for that. So with that, over to you, Oded.
Hey, hi, good afternoon, everyone. Again, it's a pleasure to join you. Thank you, Shweta, for the introduction and for inviting me. I'm sorry I cannot be there in person. I still have many fond memories from my last visit to Chennai, so hopefully I can visit the Arvind Raghunathan Center maybe in the near future. So let me get started. So I'd like to tell you about an quantum algorithm for factoring integer numbers that in some ways is more efficient than Shor's algorithm. I think I can hear everyone, so if there are any questions, feel free to just shout and I'll stop and explain. I will not assume much familiarity with quantum computation, so hopefully everything will be clear, even for those not too familiar with quantum. So let me first introduce what factoring integers is all about. I assume you know that 15 is 3 times 5, 21 is 3 times 7, 55 is 5 times 11. But what about bigger numbers like 1843, then it becomes, right, it seems to become more challenging, right? So I mean, we already get some intuitive sense that this problem of factoring integers is not so easy, and this happens to be 97 times 19. And 8051 is my next example, and you can try to think in the meantime how to do that. But there's a nice story around 8051, and this is due to Karl Pomerantz. And Karl Pomerantz did lots of amazing work in algorithmic number theory, and he shared this experience from a high school math contest. So they were supposed to factor 8051, and he thought he's pretty good in arithmetic, so he could easily just trial divide, to divide it by 2, by 3, by 5, by 7, and so on. You have to go all the way up to 90. So he thought he could do it, but he was trying to be clever. So he's trying to find a better proof or easier proof, because he thought this is surely not the way it should be done. He spent a few minutes trying to find this way, but was slowly wasting more and more time. And at the end, he did waste too much time and missed the problem. But that kind of traumatic experience actually taught him an important lesson, which is there is this trick of, you can write 8051 as the difference of two squares. It's 90 squared minus 7 squared. And once you do that, something very nice happens, because then you can write it as 90 minus 7 times 90 plus 7. And you have the factorization of 8051. And this is actually something that led him to developing some of the most powerful algorithms, classical algorithms for factoring integers. And in fact, a similar idea also shows up, as you'll see later, in quantum algorithms for factoring integers. So, of course, this is a very basic idea, the way I'm presenting it here, but it led to some really deep ideas, I would say, by Karl Pomerantz and others. So, back to factoring. Currently, the world record is factoring a 250 decimal digit number. That took an incredible number of computer years. It's incredibly difficult to factorize big numbers. Of course, you can choose numbers that can, even numbers you can factorize, but the idea, most numbers you want to factorize for cryptographic purposes are typically difficult. They don't have any small prime factors. So this is an example here from the RSA challenge. And this is currently roughly where the world record stands. So, we have trouble factorizing big numbers, at least classically. And the best algorithm, and this relates to Carl Pomerantz's work, is known as the number field sieve, developed in the early 90s. An amazing algorithm, I think one of the most beautiful algorithms out there, using really beautiful mathematics. And it runs in exponential time, not in a number of digits, but in the cube root of number of digits. That's why it's so good, because it's actually remarkably fast, relatively speaking, right? So it's not, it's really in the exponent, the cube root, right? So this is the way to factorize numbers that have 250 decimal digits. I should mention the problem is not believed to be NP hard, so we don't know. Maybe there's a polynomial time algorithm, and that's, I hope I hope people still think of trying to improve this. But this is currently where things stand, at least for the last 30 years or so. This is an extremely important problem. Shweta can probably tell you much more than I can. It's used for cryptography, for secure communication everywhere, basically, right? So, at least until recently, this was the main problem used. This and related problems like, discrete log and so on. It's really the way cryptography works. This is how we connect, HTTPS or whatnot. We use cryptographic protocols based on this and related problems. And there was a big breakthrough, a big crisis, maybe you can say, in cryptography in 1994. And this is Peter Shor, who actually realized amazingly that factoring is easy if only you have a quantum computer. So he found an efficient quantum algorithm that allows you to factorize integers. So, in principle, you could, factorize very big numbers. And that was a big crisis, I would say. It still is in some sense in cryptography, because now there is a concern that quantum computers can break all our cryptographic codes. So it's a really nice algorithm. I'll tell you a little bit about it in a few minutes. So how bad is it? Is it really the end of the world? Like now we have this algorithm, and now we cannot use cryptography anymore. I mean, cryptography is something we like to have, right? It's quite important. So, well, not so fast, right? It's not so fast, and there are two reasons, right? The first one is that there's something known as post-quantum cryptography, and that's related to lattice-based cryptography, and that's something that's here to save us. It's a different kind of cryptographic problem. It's not related to factoring, at least not directly, and that's something that slowly the whole internet is kind of transitioning to. So there are actually already many websites and browsers that use this kind of post-quantum cryptography. And just a few days ago, when was it? Like 2 days ago, I just saw this in the news, that Google targets 2029 for a complete switch to post-quantum cryptography. So there are already standards out there. I think people have some idea how to implement those things. And this is, will, in some sense, hopefully protect us against Shor's algorithm, because we have completely new kind of cryptography or different kind of cryptography that is not related to factoring or discrete log or any of those problems that Shor was able to break. So that's not the topic of today's talk, so I will not get back to it, but just to tell you that don't panic. There's hopefully alternatives to lattice-based, to factoring-based cryptography, and this is post-quantum cryptography. Okay. There's another reason why it's not the end of the world, and this is maybe the simple reason that we just don't have quantum computers, right? At least not yet, right? So you probably hear in the news that there's constantly work from industry, governments, trying to build bigger and bigger quantum computers. This is old news, 2017. IBM started building quantum computers. You see an example here. This is 2019. Google has a slightly bigger computer, the same 53 qubits. This is 2022. IBM is back with even bigger quantum computer. And this is just the most recent design from IBM, 120 qubits. It's still very, very far from running Shor's algorithm. Okay, so it's nice. It seems like they're doing some nice things, but I would say it's not clear if there's been yet the really breakthrough that will allow us to go to thousands, probably tens of thousands, or hundreds of thousands actually needed to really implement Shor's algorithm. So there are some interesting new technologies, really new ideas, conceptual ideas on how to approach this. So things do, seem to be going in the right direction, but we're not there yet in terms of quantum computers. It might happen. So, stay tuned. But just to demonstrate how far we are, this is this kind of nice diagram that I stole from Sam Japp. Let me not go into the detail because I'm actually not sure exactly all the things shown here, but just very briefly, he's showing here kind of here where we are, at least as of 2021. There are a bunch of quantum computers. They're able to, achieve a number of qubits around, maybe around 100, and the error rate around, 10 to the -2. So that's kind of where we are, and things have not changed dramatically. And where we need to be is here, because this is where Shor's algorithm is, right? So to break RSA, we kind of need to be here. To break cryptography, we kind of need to be here. As you can see, there is a huge gap still between the two, right? So that's what I was saying, the technology is not caught up yet with Shor's algorithm. There is a big gap. And the talk today, I want to show is maybe how we can bring Shor's algorithm a bit closer to reality, making it a bit more efficient, a bit faster. Let's see how we do that. That's today's talk. Maybe it's a good time for pause for questions before I go on. Okay, it's hard to pace myself without seeing you. So yeah, and I'm not even sure if I can hear you, but do try to ask questions if anything is not clear. Okay. Is there a question?
No, there are no questions. I think it's all very clear so far.
Great, thank you. So yeah, please interrupt. I don't have that much to say. Otherwise we'll finish too early if you don't ask questions. So here are the main results. So this is a theorem I'd like to talk to you about today. So let me read it carefully.
Recording in progress.
The theorem says that there exists an algorithm for factoring n-bit integers. So I will use little n to then denote the number of bits, the input size, right? N-bit integers. And the algorithm implies a quantum circuit that has a relatively small number of gates. That's the idea here. N to the 3/2, so n to the 1.5 gates. That's really the main advantage of this algorithm. In parentheses, I'd say it does this independently square root of n times. I'll talk about that in a minute. And then later, after you run the quantum circuit, you have to do some classical post-processing, polynomial time, just to output the factorization. So this is kind of standard. We typically have to do some post-processing also in Shor's algorithm, and then output the factorization. So this part is okay. It's standard, nothing unusual. The interesting thing here is that it's n to the 3/2 gates, and for comparison, Shor's algorithm requires n squared gates. Okay, I should say there's a footnote number 2 here. The footnote says that these estimates assume fast integer multiplication. Just for simplicity, you can do everything without fast integer multiplication, because if fast integer multiplication is great in theory, but in practice, it's hard to get for reasonable sizes of numbers. It's hard to get such huge improvements in integer multiplication. But that's not a big deal, because even without integer multiplication, the gap is the same. There's always a gap of square root n between Shor's algorithm and the new algorithm. So So just for simplicity, let's assume we have passed integer multiplication, so we can take asymptotically for now, for simplicity. But if you look carefully, you think, okay, something is strange because I'm telling you n to the 3 halves, but I have to apply independently square root n times. So together, n to the 3 halves times square root n is still n squared. So what did I gain, right? It seems like this is, you know, it didn't really change anything because I still have to do n squared gates. Well, the difference is that running a, you know, quantum circuit, it's something that you're very limited in, right? Because there's only that much time you can use the quantum computer before it decoheres, so before it completely breaks down, right? So the fact that you can run a much smaller quantum circuit is a big advantage. You know, physically it can be smaller, the fewer gates you have to run, the time you have to run is smaller, so also, you know, it makes it much easier to implement potentially. There are fewer gates, you know, a lower chance of decoherence, of things breaking in the quantum circuit. So time or number of gates is potentially a critical parameter. Okay, I'll get back to it much later about the practical aspects. But again, in principle, all else being equal, and it's not clear if all else is equal, but if all else is equal, a circuit with fewer gates should be easier to implement. And that's the idea here. Now, the fact we have to run it to square root n times is not a big deal. You know, just take the circuit and just press it multiple times. You know, run it again and again. That's okay. That doesn't cost you anything. It's the same circuit. You only have to build it once. It's much smaller than Shor's, and that's the advantage, right? So the idea again is this: we're trying to reduce the number of gates. That's the main goal of this talk, and I'll try to explain to you how this is done. There's another footnote here. I did not mention footnote number 1. Footnote 1 says that originally in the paper there was a number theoretic conjecture. I will not go into this. Maybe I'll mention later where this comes up. But now this is unconditional. This nice work by Pilat that showed how to remove this conjecture. Now this is unconditional algorithm. So I can, if anyone wants to hear the details, I'm happy to say more or talk to you later offline. Okay, so again, the goal is to reduce number of gates in Shor's algorithm. So before going to the technical details, let me just mention again that what does it mean in practice, right? Because this is not an easy question, for various reasons. Like it's not easy to tell what this actually means in practice. So currently, just kind of full disclosure, currently it's not clear if the algorithm can improve on Shor's algorithm in practice, right? There's some evidence that it might, but it's not clear. There are multiple reasons for that. So first, Shor's algorithm is amenable to extensive optimizations. It's actually remarkable how well you can optimize Shor's algorithm. Very clever things you can do with it. Some of them are applicable also to the new algorithm, and I'll mention later. People have done some really nice optimizations, but probably not all. Shor's algorithm is simpler, you'll see. It's slightly simpler than what I'll present today, and because of that, you can optimize it in certain ways that I'm not sure are applicable here. The gap is not... Sorry, question?
Yeah, I just wanted to ask, but I mean, this could also be an artifact of the fact that Shor's algorithm has been around much longer, right? So optimization work has been done, whereas this one may just need more time.
Yes, I would like to think so, and I'll mention later there's progress happening kind of continuously, including a few months ago. Very nice work I mentioned. So hopefully, I think we're getting there. So yes, I think so. But it's people have tried. There's still a good gap, I would say, in practice. Maybe I will show some of the numbers. Maybe I'll show later. But absolutely, it's a good point. Yeah. But I would say maybe more generally. Let me say also, it's even the question is not well defined, and in the sense that to do this kind of analysis, like what sometimes people say costing. So how much time or how many resources does it actually take to implement the quantum algorithm? This is very dependent on the hardware. because quantum architectures are very different from each other. Some architectures are very limited in number of qubits you can have, and kind of the memory you can have. I'll mention this in a minute. But some other architectures don't care. You can have thousands of qubits, but then you have other issues, right? So it's kind of a whack-a-mole kind of game. I mean, some architectures are very good in number of qubits. Some are very good in error correction, but don't have so many qubits. So it's all depends a lot on the architecture. So, when we write an algorithm for a classical computer, we kind of know what we're dealing with because we have classical computers, but, we don't have quantum computers yet. So we don't actually know what the main challenges would be once the computers are built. So I mentioned briefly now, one important metric generally in some quantum architectures is memory usage, like number of qubits. And some architectures, as you saw, like I mentioned IBM's, they're very limited in number of qubits. You only have 120 qubits on this chip. So again, it's architecture dependent. Some other architectures seem to be much more flexible in terms of number of qubits, but then they have other issues. But at least if you care about memory usage, and I will not focus much on that, but if you do care about memory usage, Shor's algorithm is amazingly efficient. Shor's algorithm can do 3n logical qubits. Okay, logical because you have to do error correction, but basically 3n qubits. The new algorithm I'll show you today requires many more qubits. N to the 3 half qubits. And as Shweta alluded to, actually there is room for improvement. And recently, this was improved to about 12n, maybe 10n, maybe even 9n. This is really nice work of Raghavan and Vaikunthanathan, and also Raghavan later separately. So they were able to improve the number of qubits. So I think it's hopefully going in the right direction. It's still not exactly 3n, but it's getting there. It's kind of amazing one can do 3n. I mean, just saving the input takes n, right? So there's really nice optimizations people were able to implement here. So I'm going to switch gears, maybe talk more about the theoretical side. Okay, so what's actually going into the algorithm? But maybe first let me tell you about Shor's algorithm. Okay, so I assume not all of you have seen Shor's algorithm, and actually even those who have seen it, I'll do it slightly differently. So maybe you'll notice a bit of a difference, because I think it's a slightly better way to do Shor's algorithm, and that's also the way that I can later show you how to extend it. Okay, so what am I showing you here? The main idea in Shor's algorithm is to look at exponentiation function, modulo, the number you want to factorize. Right? So imagine I want to factorize 8051 for simplicity, right? In practice, you want to factorize numbers with hundreds of digits. Let's look at this function that maps z into 4 to the z. I take 4 because it's just easier to work with it and visualize, but Shor takes a random number, not 4. Shor takes a random number here. But let's just take 4 for simplicity. I will also use the fact that 4 is a square, right? So you'll see it in a minute. So what I'm showing you here is just a nice graphic showing you this function, but it's kind of, imagine this is kind of a long strip of colors, and I'm just, because it was so long, I had to put it in multiple rows, but it's really just kind of one long strip. What I'm showing you this function where each, I would say, color corresponds to a value. So if you look carefully, like 0 is mapped to the value 1, and that's kind of the color you're seeing here. Then 1 is mapped to 4, right? 4 to the power 1. So it's kind of 0, 4, 16, 64, and so on. And basically, I just assign each value to a color so we can visually see that. The thing that happens, and this is really the main idea in Shor, is that this function has a period. Okay, this period is known sometimes as the multiplicative order of 4. This function at some point will basically wrap around itself, and you'll find a z such that 4 to the z is again 1, right? So we start with 4 to the 0, which is 1, and at some point we'll get back to the same value. Okay. And if you look carefully, you might see it here. So if you kind of scan it carefully, you might start seeing the same pattern here that we also had here. And after that point on, everything repeats itself. So let me try to show you that using the amazing or the only animation I was able to do. Let me see if it works. So hopefully you can see it. I'll try to show some animation now.
Yeah, we can see it.
Okay. So hopefully, was it smooth enough? Could you see it moving?
We saw it moving.
Okay,
Yes.
okay. So I apologize. This is the best animation I'm able to generate, but hopefully you could see. So the idea is that this whole chunk here is basically a repeat of the chunk in the beginning. So there's periodicity, and you can kind of see where it happens. Happens around 984, I think. So there's a point here where things become, repeat themselves. This is the multiplicative order of Z. This is the period of this function. And Shor really uses this. So what Shor basically does, and this is something you can do when you have a quantum computer, you can compute this function, this exponentiation function, you can compute it in superposition. So you can compute it somehow for all possible inputs in, the same time. And then use the one and only tool we have, which is the quantum Fourier transform. I'm exaggerating, but the most powerful tool we have, quantum Fourier transform. You use quantum Fourier transform to basically extract this period. So this is something that quantum computers really excel in, which is finding periods. So Shor uses that idea, uses the quantum Fourier transform, and extracts the period of this function. Let me just mention, you don't really have to know this, but let me mention because it might come back later. When you do in Shor's algorithm, and generally when you do quantum Fourier transform, it's not like you immediately get the period of this function. What you actually get is a multiple of 1 over the period. And it's a random multiple of 1 of the period. And so what Shor has to do, if you've seen Shor's algorithm, there's a bit of work one has to do there using continued fractions, where actually you extract the period. So yeah, I'll get back to it later, but for those of you who've seen it and those of you who've not seen it also, let me just say there's a bit of classical post-processing that one has to do. And that's standard and not a big deal. You use this continued fractions to actually extract the period of this function after you do the quantum Fourier transform. You actually have to do it twice, and then you get the period of this function. At this point, it doesn't matter, and actually you can ignore it if you'd like. I'll get back to it later, maybe briefly, but okay. So why do I care about the period? I did not say that. Let me just show you briefly. This is standard number theory. This connects to what I showed you with Carl Pomerantz actually in the beginning. This is how Peter Shor factorizes the numbers. So let me just go through the number theory. It's it's not difficult, but if you haven't seen it, it might be confusing the first time. So having figured out that the period of 4, so we found the period of this function of 4 to the power z is 984. So what does that mean? It means that 4 to the power 984 is 4 to the 0 because it's a period of the function, right? So this means that this is 1 modulo 8051. What we now learned is something very nice. So we learned that 2 to 984, not 4, but 2 to 984, this number, which happens to be 1163, this number is a square root of 1. Okay? So why is it square root of 1? Because, well, if you square it, it is 4 to 984, and that is 1. Right? This is by definition the meaning of a period of this function. So 2 to 984 is a square root of 1. And once you have a square root of 1, you can factorize 8051. Let me show you why. First, I should say it's not just a square root of 1, it's also a non-trivial one. I mean, of course, 1 and minus 1 are also square roots of 1, but this is not a square root, it's not a trivial square root of 1. It's 1163, right? So this is an interesting square root of 1. And therefore, 1163 minus 1 times 1163 plus 1 is 0, right? Because if you expand this, just like we did with Pomerantz's example, if you expand this, you get 1163 squared minus 1, which is 0, because 1163 is a square root of 1. So square of 1163 is 1. Right? So if you look at this, we basically see here that 8051 divides the product of these two numbers. So divides the product of 1164 and 1162. So which means we can use GCD now to recover a factor of 8051. So indeed, that's exactly what Peter Shor does. The GCD of 1162 and 8051 is 83, right? So we know that 8051 divides the product, but does not divide any of them individually, right? Because those numbers are smaller than 8051, they cannot divide 8051. So 8051 must kind of must split between these two. So if we use GCD, we'll figure out which of the two we'll figure out how to get a factor of 8051. So finally, 8051 is 83 times 97, and we're done. Okay, so it's basic number theory. If you didn't immediately follow this, it's fine, but that's the idea we'll also use later. So the main thing to take away from this is that we want to find, non-trivial square roots. That's how one factorizes integer numbers, and that's well known in algorithmic number theory. The goal is to find square roots of 1. Question? So I can now tell you about the new component. Okay, but before that, I should tell you why, what's the computational expensive part here. And it may be surprising if you're not familiar with Shor's algorithm. It's surprising that the most expensive step in Shor's algorithm is actually not really the quantum part. It's not the quantum Fourier transform. The most expensive step is something very simple. It's just exponentiating numbers, right? This is the most expensive step in Shor's algorithm. It's expensive because even though it's a classical function, we have to implement it in superposition inside our quantum computer. So it's a classical function, we're just mapping z to some a to the power z. And I told you this is really the core of Shor's algorithm, this exponentiation function, and Shor uses some random number a here. This is the most expensive step because you have to implement it inside the quantum computer, even though it's entirely classical, right? How long does it take? It takes quite a lot of gates. The reason is that we have to exponentiate a to a relatively high exponent. The exponent has to go up to roughly 2 to the n. So remember, n is number of bits in the input. Like 8051 is a small example. 8051 is not little n. 8051, the n would be 4 in that example, or whatever, or 12, right? N is number of bits in my input, okay? So, and the exponent has to go up to roughly 2 to the n because we want to see the period, right? We want to be able to cycle, and at least we have to see the period. So this is, the exponent actually has to be pretty large. How do we do that? Obviously, we don't just multiply a times a times a times a exponential number of times, right? We know about a trick called the repeated squaring trick. It's a standard trick, and that allows us to take a squared, a to the power 4, a to the power 8 very quickly, but it's still quite slow, right? It requires n multiplications of n bit numbers. And in total, we get n squared gates. And this is what dominates Shor's algorithm. This is why Shor's algorithm requires n squared gates. Okay? Not because of quantum Fourier transform. The quantum Fourier transform is super fast. There's no issue. This is the issue. Let me just show again in more detail how repeated squaring trick works. I assume most of you have seen it, but this will be useful later. So let's just remember how this works. I give you an example. I want to compute a to the 29. How do I do this? I don't just do a times a times a times a 29 times. Instead, I take a, I square it, I get a squared. Then multiply by a, I get a cubed. I square it, I get a to the 6. I multiply by a, I get a to the power 7. I square it, a to the power 14. I square again, a to the power 28, and I multiply by a. How did I do that? What's the idea? Well, it's basically the binary decomposition of 29 shows me, should I square, which kind of doubles the exponent, or should I multiply by a, which adds 1 to the exponent? So basically, the binary decomposition of the exponent tells me what sequence of operations I have to do here. The important thing here is that I have n operations, n steps, or multiplication steps roughly, and each one takes roughly n gates, because I have to multiply big numbers, right? Those are n-bit numbers, so I get n squared gates in total. questions so far? So let me just tell you. So this is the idea. But you might think, okay, let's try to improve it. Here's the first attempt to improve Shor's algorithm. It doesn't work, but let me tell you anyway. One idea is, let's not take A to be just a random number like Shor does. Let's take A to be a small number, right? So Shor takes A to be as just a random number, n-bit number. Let's maybe take A to be a small number like 4, like I told you before. Let's take A to be 4. Initially, you might be excited, but you realize very quickly this is not actually buying you anything, or not much at least. The reason is that very quickly, you square again, very quickly this number will become just an, generic n-bit number, right? And let me just explain. Each time you square, you double the exponent. So double the number of bits, basically. So after log n steps, you end up with an n-bit number, right? There are n steps here. This is a long process of n steps, but after only log n steps, just the number is like n-bit number, and that's it. I mean, you lost all the benefit of working with small a. So that doesn't help. Okay, it doesn't seem to help. Let me now switch and tell you about the new idea. And the new idea is to extend Shor's algorithm to a higher dimensional function. So Shor's algorithm works with a one-dimensional function, right? 4 to the power z. Okay, you have one input to the function, just z. What I'm doing now is I'm saying, let's take a two-dimensional input, take z1 and z2, and map them to 4 to the power z1 times 9 to the power z2. Now it's a function on the plane. Okay, I'm showing you a picture here. The function on the plane where every input is z1, z2, and it's mapped to a certain number modulo 8051. I should say,
hello.
What we actually want to...
Oded, there is a little black band on the top. Something is obscuring the title.
Thank you.
Yeah.
Is it better now?
No, it's still there.
It's not. Thank you. So I think it's the zoom bar.
It's gone. It's okay
completely
now.
Gone or just slightly better?
No, it's completely gone.
Okay,
what did you want?
Well, I want it to be gone. I just moved it a little bit, but if it shows up again, let me know. So what it says here now, you can hopefully you didn't lose any of the previous title, right? You can go back. I mean, it was saying Shor's algorithm number of gates, and now it's saying the menu idea, go to higher dimensions. Thanks. So in the algorithm, you actually need to do not 2 dimensions, but 3, 4, actually somewhat higher dimension. Not very high. I'll tell you later. It should be a few dozens of dimensions. But for now, let's just, for simplicity, think of 2 dimensions. And you can see the function here. And I hope what you can appreciate is, again, there's some periodicity in this function. And I intentionally chose colors so you can see some kind of pattern more clearly. There's this pattern here. And you can see it repeating here and here and here and here. So you can see that there is, hopefully you can appreciate there is this kind of periodicity happening here, but in 2 dimensions, not in 1 dimension. In fact, you've heard earlier today from Divesh about lattices, and maybe you can see this actually forms a lattice. This pattern is a lattice pattern. We actually also had it previously in Shor's algorithm. It was a 1-dimensional lattice, but we just had a period in 1 dimension. Now this is what a period looks like in 2 dimensions. I can show you again my animation, and that would be the last animation I can offer. So let me show you again that there is a period, because once I put it here, things align very nicely. So this is a period of this 2-dimensional function. So there are actually kind of multiple periods, and but there you can use this one, you can use this one. This is the main idea. The main idea is now let's try to find a period not of a 1-dimensional function, but a 2-dimensional function. And luckily, you see in the next slide, it's still enough. Once you have a period of a 2-dimensional function, you can factorize 8051 for a very similar reason. And let me show you exactly in the next slide. So it's essentially the same idea. So since the period, now we found the period of this function. The period happened to be 19,47. Okay. So what does it mean? It means that 4 to the 19 times 9 to the 47, that's the same as 4 to the 0, 9 to the 0. That's a period, right? So it takes us back to the origin. And that is simply 1 modulo 8051. What does that mean? It means that 2 to the 19, not 4, 2 to the 19 times 3 to the 47. And that's exactly why it shows 4 and 9, because they're squares. This tells me that this is a non-trivial square root of 1. This happens to be, if you calculate, this happens to be 6888 modulo 8051. And once you have a square root, just like before, the minute you have a square root, you're happy and you're done, because 8051 divides 6888 minus 1 times 6888 plus 1 for the same reason, because if you expand this, you'll get 6888 squared minus 1. So 8051 divides this product, but does not divide any of them individually, so we can recover a factor by computing GCD, right? Because we know that 8051 must split between these two. And then we find a GCD of 97, and we're done, because 8051 is 83 times 97. It's really the same idea as what we had before. Okay. So, what's the game? Let me again summarize. It seems like I just made things more complicated, right? So why bother 2 dimensions? Everything was very nice previously. Where we gained is that now, as you can hopefully appreciate here, the period is actually much closer to the origin. We found this, actually the one I chose, this one, the 47 and 19 or whatever it was. It's actually much closer to the origin than previously. Previously, you had to go to thousands, and here it's very close to the origin. In fact, it should not come as a surprise, because if you think about this, it really just follows from pigeonhole principle. The idea is that, if you're in 2 dimensions, there are way more inputs, in this region here, right? If I think of this small region here, there are, square, in the region of the square of 4 times 40, right? 40 times 40, the number of possible inputs is 1600. So just by pigeonhole, some of them will have to be equal and will have a period. So this going to 2 dimensions, kind of by pigeonhole principle, will necessarily bring some of those, will have to bring the period much closer to the origin. And that's nice, because it means that the exponent is not so big. And if you recall, that's one of the most costly steps in Shor's algorithm.
So why, there's no reason to stop at 2, right? How far can we go with this idea?
Great. Keep that question, and you'll see later. Maybe you'll catch the issue later. In fact, we will go beyond the 2. We'll have to go higher, but something will stop us, and that's a subtle point that I will try to hide, but you will maybe notice later. There's a limit. You cannot go to arbitrary high dimension. But for you definitely want to go beyond 2, and I think you want to go to something like maybe 100 or so, and I'll tell you later where the bottleneck is. Great. So, as before, the most expensive step is the function evaluation. Previously, we had a simple exponentiation function. Now it's what you might call multi-exponentiation. So now we have Z1, Z2, maybe more, maybe Z1, Z2 up to ZD. So let me use D to denote the dimension. It doesn't have to be 2, maybe it's a bit higher. And the function maps Z1 up to ZD to this multi-exponent, right? To A1 to the Z1 times A2 to the Z2 times AD to the ZD. So this is the function we want to implement now. Very similar. We just have this multi-exponent. So what's the advantage? The advantage is now that the Z's don't have to be so big. Previously, they had to be n-bit numbers. And that made it slow, because we had to do n multiplications of n-bit numbers and gave us n squared. Now we're in dimension D. And as I was saying, because of the pigeonhole principle, the period is not going to be so far. So we actually only have to raise to exponents that are up to 2 to the n over d. So they only have to have n over d bits in the exponents of z1, z2 up to zd. Right? Just if you think like combinatorially, right? You have the number of inputs you have. If you go up to 2 to the n over d, because you have d of them, it's 2 to the n over d to the power d, which is 2 to the n. So there is, you see a period at that point. Okay, that's what I was saying before. Pigeonhole. But the issue now, because this seems like it's great, we have much smaller exponents, but if you think for a second, each exponentiation now requires only n over t multiplications, which is great. But if you think for a second, we have to do it d times because we have z1, z2 up to zd. So what did we gain? Right? It seems like we gained something because I can compute ai to the zi individually, each of them, n over d multiplications, but I have to do it d times. So it seems like at the end of the day, I still have to do n multiplications. Well, luckily, this is doable. This is actually salvageable, and we did actually gain something. So it seems like we did not gain, but we did gain something. And now we have to combine this with the idea that we should take AI to be small numbers. And now this actually helps you. So the trick is to choose A1 up to AD as small numbers. And those could be, for instance, squares of the first D prime. So literally choose 4, 9, 25, 49. I can tell you something later about those numbers, but they are very, very small. Okay? Those numbers are very small. And now if you just, this is a really nice, easy exercise. This is something people have known for many years. You can compute now this multi-exponent with exponents up to 2 to the n over d. You can compute it using only n over d multiplications. Okay, so that means that the number of gates you need is n squared over d, and not n squared like we had with Shor's algorithm. Okay. So again, this suggests choosing bigger d helps us because we can reduce it from n squared to n squared over d. There is still some bottleneck. I'll mention it in a minute, but that's the idea. I still have to show how to do this. Again, this is a nice exercise, so you can take it as an exercise and just don't listen to what I say in the next slide. But this is there's a way to compute such a multi-exponent using only n over d big number multiplications. There are some additional multiplications you have to do, but of small numbers, which is not an issue. It's very, very fast. But the big number multiplication is what we have to pay for, and that's n over d only. Let me show how you do that. It's a nice exercise. So the first thing you want to notice is if you have these small numbers, like A1 up to AD, you can multiply them very, very fast. So for instance, if I want to compute A1, A2 up to A8, I should not do A1 times A2 and then times A3 times A4. This is too slow. This will take me D squared gates because I have to each time multiply by another small number. So, the numbers very quickly become D bits long because I'm multiplying D numbers. They're very small individually, right? But after I'm multiplying roughly D, they become D bits. And if I do it sequentially, it will be D squared. Instead, the way to do it is this. And again, this is well known. You do some kind of binary tree like way of multiplying. And the whole thing ends up being, if you solve the recurrence, it's something like D log D or D log square D. This is very, very fast. So don't worry about this. This is not a bottleneck anywhere, So, this is not the issue. You can compute, as long as the numbers are small, you can compute the product of them very quickly. The interesting or the important part is this, and you want to use repeated squaring, just like Shor does, but in a slightly different way. And let me give you an example. Imagine I want to compute this multi-exponent, A1 to the 13, A2 to the 9, A3 cubed, and A4 to the 6. The trick is to kind of utilize each squaring operation more than in a more clever way. So let me show you how you do that. So you start with this number, which is just 1, all the exponents are 0, so just 1. And then you multiply by A1 times A squared. Remember, this is very easy to compute. A1, A2. You multiply by A1, A2. A1, A2 is very quick to compute because those are small numbers. I can multiply them in time D. So I multiply by this and I get this next number here. Now I square, so it doubles all the exponents. I have 2, 2, 0, 0 in the exponents. Now I multiply by A1, A4. And I get 3, 2, 0, 1 in the exponent. Now I square, I get 6, 4, 0, 2. Now I multiply by A3, A4. I get 6, 4, 1, 3 in the exponent. Now I square, I get 12, 8, 2, 6. And I multiply by A1, A2, A3. And I get 13, 9, 3, 6, which is exactly what I wanted. So what's the trick here? The trick is that we don't have to do this so deeply. This is not so deep because the exponents only go up to 2 to the n over d. So the depth of this is only n over d. And the amount of time I have to spend on each squaring here is only n. So overall, this is n squared over d. Okay, so that's the idea. The exponents are not so big, and I kind of amortize somehow because I use the same squaring to on all those numbers together in some sense. Okay, so this is called multi-exponentiation, and this is a nice trick to speed up computation of things like that.
So previously, we were using the binary decomposition to tell us how to go, and how does that generalize?
So so exactly. So what? Sorry, I should have said that. So exactly what's going on here is actually the same binary decomposition. I should have said that. The reason I do A1, A2 is because A1, A2 are they give me the most significant bit. So 13 and 9 have the most significant bit of 1. That's why I do A1, A2. And the next bit is 1 in A1, A4. That's what I took A1, A4. So the choice of A's here, this is the way I choose those A's is because of the binary decomposition of the exponents. Okay. So it's the same idea.
Okay.
Yeah. So it takes some time to see what's going on here, but at the end it's an exercise. Yeah. But yeah, so I use the binary decomposition to decide on what to multiply at each step. It's okay. So the important thing to take from this is that, let me go back. Now we can do n squared over d gates. So choose a bigger d, you have a smaller circuit. But you probably realize and feel uncomfortable now because this is too good to be true, right? This would allow me to take d very big, going up to n, and I will be able to get n gates, which is amazing, right? But I told you that unfortunately it's only n to the 3/2 gates. That's currently the state of the art. We don't know how to go below n to the 3/2. And that's an important missing detail. And let me tell you what this is. So there's something I did not tell you, and that's important. In order to actually find period d dimensions, I mentioned you use the quantum Fourier transform, but it's not enough. Because when you do the quantum Fourier transform, you end up with what is actually a certain lattice problem. In fact, for those who know Shor's algorithm, Shor also has a lattice problem to solve. No one ever says this because usually we think of it as continued fractions. But continued fractions is also a lattice problem, just in kind of one dimension. What we have here is the d-dimensional generalization of that. So this is not a new thing. This was already there in some sense in Shor's algorithm in a very implicitly, because Shor's algorithm uses continued fractions. But once you try to extend to d dimensions, you realize you actually end up with a d-dimensional lattice problem. Luckily, it's something we can solve. We can solve it. This is classical. We can solve it in classical post-processing using a beautiful algorithm of Lenstra, and Lova. So I'm showing here in this picture. To do that, we actually have to run the quantum circuit d times, because each time we run the quantum circuit, let me just tell the experts, we get a sample from the Fourier transform, or namely from the dual lattice, and we need to run it d times to have a basis of the dual lattice and to be able to apply LLL. Each run gives us a vector, and then we apply LLL to really compute the full basis. But this is just for the experts. Let me just tell all of you that this can be done efficiently using the LLL algorithm. But here's the issue. This algorithm is an efficient algorithm, but it gives a rather poor approximation of 2 to the d. So this approximation becomes worse the bigger d is. So we cannot take the dimension to be too high. The dimension should be higher than 2, but not much higher, because we have to pay for this 2 to the d. And the way we pay for this 2 to the d is in the exponents. So the exponents I mentioned previously have to go up to 2 to the n over d, but actually because of the loss we have from LLL, the exponents actually have to go to 2 to the n over d plus d. And this term here is what determines the optimal choice of b. The optimal choice is n over d plus d, and this leads to the stated n to the 3/2 gates. And this is also why we have to run the circuit square 10 times, because each time we run it, we get one vector from the lattice, and we need d vectors from the lattice. So I'm slowly running out of time. So maybe still want a question, time for one question. So let me summarize. The idea is to choose A1 up to AD as the squares of the first d primes. Actually, you want them maybe a bit bigger. I can say something about it later, but those are very small numbers. You apply this quantum circuit d times. Each time you get some vector when you measure it, and you do some classical post-processing using LLL to recover the period. Once you have the period of this lattice, you can factorize n using the same idea that Pomerantz had. So that's roughly how things work. It's basically a d-dimensional extension of Shor's algorithm, right? If you think about this, there are some bells and whistles, but at the end of the day, it's a d-dimensional extension. I mentioned briefly follow-up work. Previously, let me also mention that the idea has been extended to discrete logarithms, work of Ekara and Gardner. There's a interesting trade-off happening here. Actually, it's a funny thing to mention with classical lattice algorithms. If you're willing to spend more time post-processing and running a lattice algorithm longer, you can actually reduce the resources that the quantum algorithm has to do. So it's a nice trade-off. There's some work discussing this. In principle, I'm happy to spend, a month on my classical laptop and reduce the size of the quantum algorithm. So there's a fun trade-off you can do here. I mentioned previously memory reduction. So the latest state of the art is around 10n, 10 times n qubits. They also deal with other issues in this nice paper. So Raghavan and Vaikunthanathan. And finally, this is very recent work by Kahanamoku, Meyer, Raghavan, and von Kerk. They did further improvements of the memory using something called spooky pebbling, which is a really nice idea. You can look in their paper. And that's basically it. I'll thank you here. Maybe there's still a minute for a question. I'm happy to elaborate on everything I skipped on shove under the rug. Thank you for the attention.
Thanks a lot. Are there any questions? Yes, 1 second.
So you mentioned some number theoretic conjecture that is used for proving that theorem. So I don't know that it didn't come up in the.
Great. This is one of the few things I was trying to hide. Great. So in the algorithm I showed you, I told you, let's take small numbers. Let's take the AIs to be small numbers. This is actually not something that you can just do like that, because there is a concern that maybe small numbers will unfortunately always lead you to trivial square roots. I mentioned that one of the things that Shor's algorithm and also this algorithm must ensure is that you find a square root, which is great, but the square root must be non-trivial. If the square root you find is 1 or -1, that's not useful, right? You need to find a non-trivial square root modulo the number you want to factorize. So it turns out when you choose the A's to be random, that's very easy to prove, and Peter Shor did that. It's very easy to prove that when you take random A's and then use this algorithm, you will find non-trivial square root. When you take A to be small, it's not trivial. So we tried to argue that small numbers are actually work, and we couldn't. So that's why there's a conjecture in the paper. Later, Pilat came and actually was able to prove it, and was showing that small numbers can be chosen and still will lead to non-trivial square roots with high probability. So that was very nice proof, and not even using any Riemann hypothesis. I think, if I recall correctly, I think it was really unconditional, but I might be mistaken. He had actually to change a bit the algorithm, so that's a nice result. But yeah, so maybe that's a longer answer than you hope for. But yeah, it's something about the small a's and how to make sure small a's still work and give you square roots, non-trivial square roots.
Thank you, sir.
So if we, in Shor's original algorithm, if we take A's to be random, then the probability of A being a quadratic residue is around half. So if I increase the dimension to 2 or more than that, the probability keeps on decreasing with the dimension. So
Yeah.
it being a quadratic residue, the if the
Yeah.
probability decreases, isn't that an
The-
issue?
So yes, fantastic question. So it is an issue, and if you notice, I actually deviated a bit from Shor's algorithm. So Shor's algorithm just chooses an A and hopes later that A happens to be a quadratic residue, and you can therefore take the square root. If you notice, I kind of preempted this. So I chose A to be 4. I chose A to already be a square. That's a small twist on Shor's algorithm. And in Shor's algorithm, it doesn't matter, as you were saying, because with high probability or probability half, it will be a quadratic residue. Here it was critical. You're right, because in D dimensions, the chances of all of them being quadratic, all the numbers is very small. So I think, I think you're absolutely right. I think it's an issue potentially, but luckily there's an easy solution, and that's the reason I'm choosing all the numbers A to already be squares. So I'm ready. I don't have this issue. I already know the square root of those numbers, so I'm kind of protected against that. But that's indeed a very subtle but very important point. Fantastic question. Thanks.
Just a small clarification that you said that we can choose A randomly, but in the final summary, you said that we take the AIs to be these first root n many squares of primes, right? So is there a relationship between the two?
Yes. So sorry, this is partly me trying to simplify things and maybe oversimplifying. So the algorithm for efficiency must have small a's. Right? You cannot have like arbitrary n-bit number a's. Then all the efficiency gains are gone. Right? The whole idea is that a's are very small and we can quickly multiply them together. For correctness, to prove correctness, this poses a challenge because the correctness proof in Shor's algorithm requires a's to be random numbers. So, as I was previously alluding to, in the original paper, I had a conjecture saying that even though the a's are small numbers, the correctness still holds. And this paper I mentioned briefly in the beginning, a paper by Pilat, he showed that it's still okay to choose small numbers. You can still choose small a's, and you will get the desired properties in terms of having non-trivial square roots. So so there is something to prove here. It's a number theoretic statement, but initially we were comfortable with this conjecture because it was consistent with everything we know, and we could test it in some sense. So we thought the conjecture is reasonable, and luckily it was proven. So now we know that the algorithm can be made unconditional. Does it answer the question?
Yeah. Thank you.
Okay, thank you.
So let's thank the speaker again.
Thank you, everyone.
Thanks, Oded, for a great talk. And we have a small memento for you, but we'll have to find a way to get it to you.
Very kind of you.
Meanwhile, thank you very much for joining us. And thanks.
Thank you. Bye-bye.
Bye.